This is an introduction to biostatistics, and we're in chapter 5, sampling distributions. And let's jump to 71. Now, quickly, a random variable is, in many classes, they define it as something that's unknown until you conduct your experiment, right? It's a random quantity that you observe. Now, from a purely more mathematical standpoint, there's one step that's often left out, and that it assigns a numerical value to that outcome. And if that's the case, then it's a random variable. Now, a statistic, on the other hand, it's a function of your observed data. And your observed data are random variables. So meaning that your statistic is comprised of random variables, which means itself is a random variable. So since a statistic is a random variable, it has a mean. The random variable itself, like x bar, we don't know that before we conduct our experiment. It's a random variable. And since it's a random variable, it has a mean, has a variance, has its own distribution. And that's what we're going to study in this chapter. And ultimately, we're going to make reference to the central limit theorem, which we'll get to in a second. Now, studying the sampling distribution, it's absolutely critical to understand so that we can make valid inferences towards the population. So we have to understand what our statistic, I almost said sample statistic, but it's the same thing. Okay, so we're going to illustrate this with an example. So we're going to have a population that just consists of the integers 1 through 20. So that means our population has a size of 20. And we're going to create all possible samples of size 10. And then we're going to look at the sample mean and the sample variance. So since the mean and the variance will differ between these, all possible samples of size 10, there's variability, but it has an overall mean, has an overall variance, has a distribution. And so we're going to look at a histogram of the sample means and variances and illustrate that it's sampling distribution. Okay, so let's do it in a little R simulation. So the population size is n. We're taking sample sizes of 10, and we can calculate that knowing combinations formula. There's going to be 184,756 different possible samples of size 10 from our original population of size 20. So let's create the integers. So this will be our population, the numbers 1 through 20. And this function here is pretty cool. What it does is it takes whatever this object is, in this case it's the numbers 1 through 20, and it calculates all possible combinations of this size, R. So of the 20 original observation, the sample population size, it finds all possible samples of size R. Then it calculates the mean. And so that's it. And so then we're going to store all possible means of size 10 from this population of 20 in this variable x2. Now we can look at the mean of our original data, that's 10.5, and we can calculate the variance of our original population. Now notice that we had to, since we know the population size is n, we have to multiply by n minus 1 to get rid of the divisor there. Then we multiply by n. So this is the population variance, 33.25. Now let's look at the mean of x2. Now what is x2? It's a vector of mean values from all the possible samples of size 10. So this vector x2 it's a vector of that length. So it's a big vector. And we can calculate the variance associated with the sample means of 1.75. We can calculate its standard deviation of the sample means, and that's actually called the standard error of the mean, which is 1.322, etc. Now, there's a formula that we use is we take the population variance, divide by R, and this is what's called a finite population correction factor, and we'll highlight that a little bit later in this chapter. And notice that those are the same. So that's the square root of the variance of our sampling distribution, and it equals. Let's look at a histogram of the sample means, and this is it. And if we were to plot over the top a normal distribution, it looks quite normal. Now let's do this for the sample variance. So again, this combinations in is take all the values in this vector, which are the numbers 1 through 20, creates all combinations of size 10, and in those take the variance. And let's look at a histogram. And this is the distribution of the sample variance. And notice that that's how many possible variance values there are of the population of 10. Now, here's the big note about this, that we had a sample size of 20, and there's almost 200,000 unique samples of size 10. And so for moderate population size, this approach is absolutely not feasible. So we have to develop a better way. And in most cases, we develop what's called an approximation to the sampling distribution. Now let's look at the sample mean, the distribution of the sample mean. Wait, how can you describe the distribution of the sample mean? Well, the sample mean is a random variable. If it's a random variable, it has a mean, has a variance, has a distribution, and that's what we're going to look at. Here's some key characteristics. If the population is normal, then the sampling distribution of the mean is also normal, regardless of sample size. Now, if the population is not normal, then it tends to be a normal distribution. And it's really true as the sample size increases. And that's due to what's called the central limit theorem. Under some pretty mild conditions, the sample mean from any distribution converges to a normal distribution. And then we can make use of that and make inferences. Now, the mean of the sample means is equal to the population mean. And that's what this is. So the capital E means expected value, or the mean. So it's the mean of the sample mean is equal to the population mean. Now, the standard deviation, or often called the standard error of the mean, and denoted by this, so this is, of course, the symbol for standard deviation, and the subscript x bar means it's the standard deviation of the mean, often just called the standard error of the mean. Now, if your sample size is relatively small compared to the population, then the sample standard deviation of the population, or the sample mean, is sigma over n. Now remember, sigma is whatever the true standard deviation is of the population, and then we divide by the square root of the sample size. Now, if the sample that we're taking is not, is larger, it's large relative to the population size, we have to put in what's called a finite correction factor, a finite population correction factor. And this adjusts. And that's what we did in the simulation above, is we added in this finite correction factor. And that's it. So this is the standard error of the mean. Now, effects on sample size, and as one expects, larger sample size narrows the distribution, meaning there's less variability in the sample mean. And if the sample size is sufficiently large, and this condition is generally accepted. I've seen some books say 25, But if the sample size is 30 or more, then it's a great rule of thumb that the sample mean follows a normal distribution, even if the population was not normal. So the central limit theorem, it's given a population of any non-normal functional form, and it has mean mu and variance sigma squared, then the sampling distribution of the sample mean, computed from the samples of size n, will have a mean of mu, the original population, so it's unbiased, and it has a variance sigma squared over n. And that's assuming that n is large, at least 30. So let's assume, as an example, let's assume that we have a single fair die and it's tossed 30 times. And let x denote the number obtained per toss. And so x is a discrete uniform, right? It takes on the values 1, 2, 3, 4, 5, 6 with equal probability. But when we toss it 30 times, now we have a sample of size 30. Okay. Oh, in a second. So the original mean of this population is 3.5. And that makes sense, right? Because if the values that we can assume are 1, 2, 3, 4, 5, or 6 with equal probability, then that, in quotes, middle value is 3.5. And that makes sense. And then we can show that the variance of a discrete uniform is 35 over 12. Now, the question, is X normal? And it's absolutely not. It's a discrete uniform, right? And if we were to plot the distribution of X, it would look like this, right? So the probability mass function of a discrete uniform in this dice rolling experiment is it can assume the values 1 through 6, and it has equal probability of 1 divided by 6. Now, using the central limit theorem, what's the distribution of X bar? Now, the key point here is using the central limit theorem. So X bar is approximately normal, and it has this. So the mean of our sample mean is the same as the population mean, which is 3.5. And the variance of the sample mean is the variance of the original data set divided by n. And so it's 0.0972. So now we can make probability statements associated with the sample mean in this context. And without the central limit theorem, that would be, it gets quite difficult. So the probability that our sample mean is 4. Now, what does this even mean? We just rolled the die 30 times, and then we calculate the sample mean. And we want to know what's the probability that the sample mean would be greater than 4. Well, since X is a normal, or at least approximately normal, if we subtract the mean and then divide by the standard deviation, this is a standard normal random variable, and this value comes down, and we can transform this into something different. So this is equal to 1 minus the probability that Z is less than 1.6063. And then we write it like this because then we can write it in the standard CDF format. So that's the CDF for a standard normal. And then we can show that we can calculate it like this. So how would we find this value? Well, those values, the CDF values, are tabled in the back of a book, or you can use R. Well, this is how we'd solve this problem in R. So P norm, so that's the CDF, and we want the so CDF accumulates from the left, but here we're saying, hey, accumulate it from the right. So we want 4 or greater. We have a mean of 3.5, and this is the standard deviation. And notice those are the same. Now, we could have converted this to a standard normal, and we get the same thing. Now, we can use exact calc. Like, so here, I round, all these numbers are rounded. And so if we put in the exact numbers, So 35 over 12 was the variance of our original population. We're dividing by the sample size, taking the square root, and then this is the exact, I say exact. Remember, it's a normal approximation, but we're using exact calculations for the standard error of the mean. And notice that they're really, really close except for a few decimal places. So rounding it is okay, but if you're using R, why not use the exact values? And again, this is using where the mean is 3.5. So this we're using the standard normal distribution. But we could have used it in just the normal distribution with a mean of 3.5 and whatever this standard deviation is. So let's simulate this calculation. And the reason I'm going to conduct a lot of simulations throughout this whole lecture, because I think it's so important for statisticians to understand and learn and be able to conduct simulations. And there's different train of thoughts in conducting simulations. And over the decades, I've learned some shortcuts, and I just want to share them with you. So I'm going to download this package called Extra Distribution, and the reason is it has a built-in function for the discrete uniform distribution. Okay, so we're going to do 100,000 simulations of this dice rolling experiment, and each experiment we're rolling it 30 times. So we're going to roll the dice 30 times, calculate the mean, and we're going to do that 100,000 times. Okay, so here what I like to do is to vectorize all the results. A lot of people will conduct a for loop, and it's equally valid, but it's much slower, and that's why I try to vectorize it. So in row 1 and row 2, okay, so I'm going to create a matrix that's 100,000 by 30. Okay, so we're going to roll the dice so many times that it fills this up. So the columns will be 30. So there'll be a 1, a 2, a 1, a 4, and there'll be 30 rolls here. And then we just roll the dice 1 through 6 here, and then 3, and then all the way to 100,000. And that last row represents the last experiment. Okay? So that's what is in simulation rolls. Now, this is a big fat matrix, but R can handle it. And what we want to do is take this matrix over the first dimension, which is rows. We want to calculate the mean. So this function goes by row and calculates the mean of the first 30 observations. Then it calculates the mean here. Then it calculates the mean here. And it does it 100,000 times and takes this vector and puts it in the mean values. Well, now let's go in and just see which ones are greater than 4. And this here creates true falses. It's a true if the mean is greater than 4, it's a false if not. And if you sum those, it's like summing the components that this is true. And if we divide by how many reps, well, that is our simulated value. That's the simulated value for the mean being greater than 4. Okay. The central limit theorem, we got 0.05, so 5% or greater. In our simulation, it's 4%. And to be quite honest with you guys, I trust the simulation results more. The central limit theorem is an approximation, and it's perfect as n goes to infinity. But on the smaller sample sizes, it's a really good approximation. And so I would trust this simulation more than the central limit theorem in this example. As N increases, of course, those two would agree. Now let's look at the difference between two sample means. And it's the same thing. So we have, let's just look at some examples how we would use this. A researcher wants to compare the average study hours per week between two groups. Group one is traditional. Group two is they use some sort of AI-assisted method. Let's say we're conducting a clinical trial that compares the mean cholesterol levels after treatment. So group one is they took the cholesterol lowering agent, and group two is placebo. And we want to compare the means between these two populations. Okay. Let's examine a hypothesis test evaluating whether a new antibiotic effectively lowers the Mobiluncus bacterial levels in bacterial vaginosis compared to the standard of care. So we're going to compare the mean bacterial levels between the two groups. This is the group that took the new antibiotic, and this is the standard of care. And the Mobiluncus is it's the bad bacteria in this infection. Now, again, we want to study the distribution of the differences between these two sample means. And that's going to help us make an inference towards the population mean. And let's see how much we got here. Okay, so it's been 21 minutes. We're going to stop here and just pick up in the next video.